Citation focus on spaceborne sparse side imaging model design, theory to implementation. Start with a brief introduction to the research background. About 70% of the Earth's surface is covered by oceans. These vast maritime regions require high precision and wide area observation. The increasing demand for resolution and widespread have led to increased system complexity. Our two fundamental theories for microwave imaging, the Nyquist semblance theory and radar resolution theory, dictate the system complexity. Therefore, it is necessary to explore new methods to address this issue. SAR is capable of observing seasons under all weather and day and night conditions and holds substantial application value across a wide range of fields. Next, I will introduce the conventional SAR imaging mode. Some common radar imaging modes include scan, tops, spotlight, sliding spotlight, and music. The relationship between the resolution of each mode and the streaming angle rate is shown in the figure. It is seen that with the streaming angle rate increasing, sliding spotlight has the highest resolution, followed by mosaic, strip map, and scan, with tops performing the worst. The actual data of different SAR imaging modes can be written as this equation. The theoretical calculations of the azimuth ability to signal ratio ASR differ among these modes. The calculation of reach ability to signal ratio RASR is the same. Next, I will introduce the sparse SAR imaging mode that we have designed. This is the workflow for sparse SAR mode design. First, based on the SAR mode, determine the corresponding platform parameters, radar parameters, and waveform parameters according to the application requirements, such as the azimuth and range resolution, ambiguity. Design waveform parameters for sparse mode. The antenna pattern suited to the space of SAR mode is constructed. Imaging performance of the sparse SAR mode is evaluated to ensure that the system meets the mission objective. In the aspect of beam position design, the choice of PRF takes into account the limitation of transmit and media interference. The timing diagram depicted in the figures present the beam position design for strip map, spotlight, sliding spotlight, scan, tops, and mosaic. The blue line represents the sparse imaging mode, and the red one represents the traditional mode. Specifically, in the sliding spotlight mode, based on the result of beam position selection, we have designed the fundamental system parameters. The plus repetition frequency (PRF) have been reduced to half of its original value. We can analyze the ASR versus the PRF under different streaming angles. Results show that the change in ASR become more obvious with the PRF increasing. The ASR increased by about 50.2 dB in sparse sliding spotlight mode, resulting in serious atmospheric ambiguity. But the next normal regularization-based sparse imaging method can solve this problem. The middle finger shows the change in ASR with the strain angle. It is seen that when the strain angle is above 1, ASR deteriorates about 8.6 dB in traditional sliding spotlight mode. But when the streaming angle is equal to 1.2, the change in ASR is less than 2 dB in sparse mode. So, the sparse sliding spotlight mode effectively reduces the effect on ASR from the streaming angle, which means that it can achieve higher quality images compared to the traditional mode. The right finger shows the variation in ASR with PRF. The sparse sliding spotlight mode can reduce ASR about 10.7 dB. This means that it can obtain a higher quality side image. In the scan mode, the basic parameters required by the system are designed based on the results of beam position selection. The PRF is reduced to 3/4 of its original value. The relationship between ASR and PRF for SS1 is shown in the left finger. It can be seen that ASR value increased with reduced PRF. It is necessary to suppress the atmospheric ambiguity using the sparse imaging method. The ASR of scan mode is collected in the same way as in strip map because the scan mode has no extra processing in the range direction. The relationship between ASR and the incidence angle for each subspace in traditional and sparse scan mode is shown in the middle finger. The red line is the traditional scan mode and the blue line is the sparse one. It is seen that the ASR of each subspace of the sparse mode is lower than that of the traditional one. Then we will take SS1, for example, to analyze ASR. The relationship between ASR and PRF for the SS1 is shown in the right finger. It is seen that in the sparse mode, the range ambiguity is suppressed. The relationship between the atmospheric ambiguities and their corresponding spectra is as shown in the finger. In our design mode, the ambiguity is centered at FDC plus or minus PRF have the most significant impact in the imaging results. We can use this relationship to specifically suppress the ambiguities. The frequency of ambiguity areas can be suppressed at this equation. By considering the atmospheric ambiguity turns into the sparse side imaging model, which can be suppressed as this. We can obtain the scenes by solving the following L2Q norm regularization problem. To validate the performance of the design mode, some experiments are performed based on the parameters of the design as sliding spotlight and scanline. Figures show the recovered images of different kinds of scenes by MF, L2 norm regularization based and L2Q norm regularization based methods from the collected accurate of the design source mode. The MF-based image recovered from the data collected by the traditional sliding spotlight mode is also given. For the design source mode, it fails to recover the sparse scenes with obvious ambiguities. The recovered image of the actual norm regularization-based methods are well focused with better performance. However, they still suffer from the advanced ambiguities. The proposed method achieves well recovery of the scene, even when the data are collected with a reduced PRF in sparse mode. To further verify the proposed method, the target to ambiguity ratio (PAR) and target to background ratio (PBR) are introduced to evaluate the ambiguity and noise separation ability of different methods. Finally, the proposed method combines the advantages of traditional imaging modes and sparse signal processing. Compared with traditional mode, the design sparse mode achieves wider sparse coverage, reduced data volume, and lower ISR without hardware changing. The used L2Q norm-based method can obtain unambiguous images of large-scale areas with reduced power. That's all my presentation. Thank you.